with this terminology here. The term interference and diffraction sort of blended together, and it can become very confusing what we're referring to. And I mean, it will suffice to say that, from my opinion, the way the terms ought to be used, not how they're actually used, is interference should be two sources, combining two sources together in some manner to produce a constructive or destructive signal. It's interference. Diffraction should really refer to sort of a self-interference. That's why we talk about the double slit experiment, we refer to that as interference. And when we talk about a single slit, we refer to that as diffraction. So the fact that this is called diffraction is not really true to the name of it, but it's a widely used term, so we just go with it. But the idea is this. We finished off the last lecture by saying, what if we get crazy and put in 3 slits? What about 4 slits? What about 5 slits? And then I think we had a problem where we did like 8 or 9 or something slits. 8 slits, I think it was. Well, what you could do is you could machine manufacture, and we have these, again, I keep saying this and I should just shut my mouth here, but we got some cool toys on campus here, and one of those toys is what's called the diffraction grating. What it is, it's slits that have been etched out on, typically it's like a real thin sheet of glass or something, and you etch these lines on there, and you could fit tons of lines. In fact, the ones we have hundreds of lines per millimeter. That's how closely spaced the slits are, and you just have tons and tons and tons of them. And of course, that's going to produce for you your interference patterns. Okay. And, the same principles are going to apply here. A wavelength comes in, and when it exits out of the slits here, it's going to diverge away, and any places where there's overlapping wavefronts are going to be interference patterns, constructive and destructive, and so on. All right. Now, the location of the fringes that occur on here, this is review. This is nothing new you're learning here. D sine theta, where what's phi here? D sine phi here, where phi can be different values of m. And so we actually have different angles here that correspond to different orders. We use the term that we use for m are orders, right? So I've actually stuck in a phi sigma, phi lowercase m here to indicate the locations in angles of these things. And of course, the actual positions on the screen in terms of a measurable distance is given by this this relation down here, the tangent. So here's where it gets interesting. We've described monochromatic light. So monochromatic light come in, and the path length differences, right, are going to correspond to where the fringes are. What if we don't let monochromatic light in? What if we let all light in? So here's what happens here. You get a fringe located at, say, Y1 here, right? And say that would be, I don't know, say it's going to be bluish light, right? Well, if we take the same order, but we consider a different wavelength, what if the wavelength was red instead? That's a longer wavelength, so it's a greater angle. And so blue light would hit in a certain location, and then red light would hit a slightly different location. Because the patterns, the interference patterns that we see, do have a wavelength dependence. So now we're looking at path length differences, but now we can consider path length differences for a whole slew of wavelengths here. And the way that this is made is we actually create a system where the fringes just naturally are very spaced out from each other. Okay, very spaced out from each other. So this is the grain here on the left-hand side, and so what happens is different colors hit different areas corresponding to whatever wavelengths they are. And what that creates is it creates a spectrometer. It creates a device that can work like a prism, because a prism will do a similar thing, right? A prism will take light and have it pass through a medium, and depending on what the wavelength of that light is, it refracts a little differently because the index of refraction is a little bit different. And so a prism does the basic principle of dispersing light. Prism's not a good mechanism, though, just because it's difficult to control the intensity of that light. Whereas you can control the intensity of light pretty easily here, but if you just have a lot of really fine slits, you know, remember from the last lecture that the more slits you pack in, the maximums get sharper. I like that language, sharper. So they become much higher in intensity. And so it's much easier to create brighter signals there. So that's what's happening here. Our blue is displaced a little higher than the purple. And same thing down here. Again, blue is a longer wavelength than purple. So we'd expect the angle to be a little bit larger. And this is interesting when you have discrete emission lines. Like putting a rainbow of colors in here is kind of confusing. You just get rainbow, 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 and it's not that interesting. It's interesting when you put a lamp through or something. You know, like we have, I mean, on campus we use sodium and krypton and mercury and neon and hydrogen and a bunch of other things that have simple visual wavelength spectra. And so what pops up here are the patterns of those lines. And what do we do with that? There was an experiment we did. I don't even remember. It's been so long since I've done them. All right, let me ask you a question here about this. Diffraction pattern produces an interference pattern on a screen if the number of slits in the grating is increased. So the number of slits of the grating is increased with everything else, including slit spacing, the same. What do you think's going to happen? All right, well, see, it is, right? So increase the number of slits, brighter fringes. Hi, I'm teaching. You gotta go. Yeah, the fringes don't change because the fringe positions change based on one of two things: wavelength differences or slit spacing. Right? It's d sine theta m lambda. If we increase the number of slits, you still have the same situation there. All right, great. All right, first example here. We want to find the angular limits of the first order visual wavelength spectrum produced by a grating with 600 slits per millimeter when white light falls upon the grating. All right, so the idea here is we have a range of wavelengths. Scout, you gotta go, okay? Scout, I'm trying to teach right now, okay? And you can't make noise. Don't make noise, okay? Okay, sorry about that. So the idea is that having a range of wavelengths should produce a range of angles, right? And so we're trying to figure out what the range of angles is. Now, when they use the words order here, first order, second order, so on, you will choose values for m to be 1, and then second order is 2, and third order is 3, and so on. Oh, so we know what our equation is, right? The only thing that we don't really have directly is what is our slit spacing? Well, we basically do have that, right? Because if we have 600 slits per millimeter, all we got to do is flip that number. This is slits per millimeter. If we flip that number, then we get a distance per slit, which is, guess what? it is the slit spacing. All right, so anyway, I was saying about the slit space, and you take your slits per millimeter, which I'm indicating with the capital N here, number of slits per distance, and we're going to flip that number. Now, it's in millimeters. You're going to want to convert that into meters. To get, now this distance here is going to be, it's meters per slit. So that is what the slit spacing is. So now we're going to go, and what we're going to do is we're going to take our range of wavelengths here. So we'll go with the 750 is going to have the largest angle, and the 380 is the smallest angle. This is a little bit outside visible wavelengths, but we'll just go with it. And I got for a M of 1, a first order, that the higher wavelength is 26.7 and the bottom is 13.2. So if you really had completely white light here, and spanning from 26.7 to 13.2 in angle, you'd see a rainbow. See a rainbow there. Now the second order, we plug in 2 for this, and we notice that we have another set of wavelengths, set of angles here, and there isn't an overlap. The second order, or the one where the second's gonna, have the interference thing, is 27.1, which is just a tad above this. So right after that sort of reddish color that would be there, you'd see another rainbow. All the way to 63.9, you could do third order. Third order does have overlap, so that's a little bit of a problem here, but you generally don't need to worry about higher orders when you're actually using this kind of equipment here. There's quite a bit of overlap between the first and the first angle here and the last angle there. And then if you go high enough, you don't have an upper limit. What happens is the highest angle you can have is 9 degrees, and these numbers will produce something larger than that. So anyway, third order is an overlap. Second order doesn't. It's interesting. And the first order is totally clean, so everything's good with that. And depending on how far away your screen is, you can define a resolution to this, right? I mean, each wavelength, corresponds to what distance on the screen. If you figure out, I got a screen 2 meters away, you work out a range of Y values, you can work out effectively like a for that. That's kind of cool. All right, let's get back to this. All right, another example here. Sodium lamp, 1,000 slits per millimeter. Interference pattern, 1 meter away. 2 bright yellow fringes are visible at this and this from the central maximum. What are wavelengths of these 2 fringes? All right. Okay, let's check it out. Now, sodium produces this doublet. That's what it is. It's a doublet at these 2 positions. And then based on the information here, we could figure out what those angles are. And then, therefore, what the wavelengths are. So let's do it. All right, so hey, she's supposed to be outside. You guys are cleaning up the glass.
No, I was talking to the letter outside.
All right, so our N is 1,000 here. Slits per millimeter, so that's going to give us a D value of basically a micron. So each slit is separated by 1 micron. And what we could do here is we can take the positions and the screen distance and turn that into angles based on the tangent. And that's, just to be clear about that, just go back to the slide here. I'm doing the stuff that's down here right now. Okay. So I get a range of angles, and it's hard to see this down here. I'll zoom in a little bit so you can see this. But that is 36.08, 36.13. Those are the angles there. And then we put this through our equation. These are going to be I'm assuming they're first order. I would be shocked if they're not. But for first order, that corresponds to 589 and 589.6 nanometers. So that's interesting because at least in this setup here, there was a good millimeter between those lines. So that means they were clearly visible. And I mentioned something about resolution previously when we can talk about that here, because this is it's less than a nanometer, less than a nanometer difference. And when it's displayed on a screen, it's more than a millimeter apart. That's kind of big. So we talk about a resolution, and the resolution would be defined as the way we define it is the wavelength that we're particularly interested in divided by what's the smallest increment of delta lambda that you can see. And you want to solve for this delta lambda. That's the idea. The R value is the same as the slits per millimeter here. So, what we do is we set that equal to. Wait, did I say no? Wait, hold on. No, I'm getting myself confused here. Sorry, no. Back up. Sorry. The resolution is lambda over lambda, delta lambda. That's equal to n times m. M is the order, n is the slits per millimeter. It's not r. And so we solve for the delta lambda here, and we get 5.89 times 10 to the minus 10. That's basically almost 0.6 nanometers, which is basically at the resolution limit here. The delta lambda comes out to 0.6 nanometers, and what that's telling us is that anything closer together than 0.6 nanometers, they will blend together. It'll be very difficult or impossible to actually see that there are two separate lines there. There's going to be some noticeable differentiation between those two lines. Okay, so anyway, lambda over delta lambda equals n times m. M is almost always 1. You put in your resolution here of 1,000, and you go with that. Okay. Now, R and n can be equal to. They usually are equal to each other when m is 1, but higher orders end up having a different resolution to them because you are producing the two wavelength difference. The angles are much further out, and so it becomes a little bit harder to see that. Well, wait a minute. That's a different factor, actually. Now, the higher orders will have a better resolution, actually. But they're harder, just practically, they're hard to see because when the angles are that big, the intensity of light gets really low, and there's another issue there, but that's beyond our points here. All right, let's get to this then. All right, so just to mention another type of technique here, reflection gradings do a very similar thing where you have a surface that is like etched like this. And when incident light comes in, the light reflects off, but the light will be reflected off at different angles. Excuse me. Depending on what the wavelength of that light is. And so when the light reflects off here, it can produce a similar effect. If there's like a path length difference. So, one beam can hit down here, another, say, red wavelength can hit over here. And depending on what that distance is between them, there's a path length difference. They reflect off, they can come together. So it has a lot to do with how finely spaced these things are and how much the path length difference is going to be. So there's a similar idea that's used in X-ray imaging, which I have a little thing to say about that at the end of this lecture. But one of the more popular ways that this is seen is, a lot of animals have very fine. It could be basically as fine as fur, feathers, things like that produce this effect. If you look, under a microscope at this thing, what we see is that we have tons of these long molecules that go across, and that can act as that reflection gradient there. So we get different colors based on the angles that you look at it. So, all right. Now, another side application here is to consider not rectangular slits. There's a lot of applications that utilize circular apertures. The most direct example is in astronomy, when we want to determine what the resolvent power of a telescope is. That's really based on the aperture and what happens is a diffraction effect takes place, no matter the size of the aperture, and puts an inherent limit on what can be seen. So, for the purposes here, we're assuming that the distance, the image formation that we're considering here, is very far away. So, I mean, this is obviously true for like a star or something like that, something's very far away. And d represents the diameter of the aperture. If it's a telescope, it'd be like the mirror or the lens or whatever. And so what happens is in the very center, so, you know, the fringes we've seen are like these rectangular shapes, which, you know, that's kind of as a reflection of what the slit looks like. For circular apertures, the circular apertures, they have a similar interference patterns. They look like circles. They're rings, basically. The center is always, there's a bright spot in the center, and then you have your first minimum outside of that, then you got your maximum. You kind of saw a little bit of this in the lab that you did earlier today, seeing the circular sort of nature of the wavefronts. And it turns out that the very first minimum that you get, so this is, when I say minimum, what we're really saying here is, you know, what the radius of that bright fringe is in the middle. Well, first minimum is given by this angle here, 1.22 lambda over d. Now I'm just kind of throwing this equation at you here, and I'm not exactly explaining too much about it because it's really beyond the scope of what we can do here. This comes from a very complicated set of functions called Bessel Functions. And this is the first solution to the Bessel function, and it's where the 1.22 number comes from, ultimately. But what this is, this gives you effectively a angular size, in a way. And so if you double this number, which we have down here, that actually gives you the diameter of that first diffraction dot in the middle. And every source of light has something like this to it. It has some kind of inherent resolution to it. And this is, you know, what's the wavelength of light you're looking at, and what's the aperture that it passes through. That will produce a diffraction pattern. And this angle that's here is effectively a resolution limit. That's the smallest detail that you can see in an image. Yeah. So it's kind of cool. So here's how these fringes look. Bright circle in the middle, ring surrounding it. Each bright ring represents an order, right? This is the first order, second order, and so on. The middle is just the central fringe, we say. And the angle that we define here is the angle from the center. I'll annotate this. It's from the center out to the first minimum. So that's the radius of that center spot there. And yeah, it's the radius of that center spot there. So you double that, that gives you that distance there, the angular size at least there. Okay. Great, great, great. All right. So we got a helium neon laser. It's a nice red light. It's pretty bold red, actually. And we're going to pass it through a 0.5 millimeter diameter hole. How far away should our viewing screen be placed in order to observe a diffraction pattern whose central maximum is 3 millimeters in diameter? Not bad. Let's get into it. All right. So we're told that the central maximum is 3 millimeters in diameter. All right. Okay. So that's our W here, and so we have our 2.44 lambda d L over d, and what we're going to want to do here is I think I skipped a step. Hold on. Oh, I didn't mention it down here, but if you combine the earlier relationship with the tangent, you can translate between angle and position on the screen. And so the W here, that represents the diameter, which is twice y1, which would be the position above, and then also below. That's why we double it. We change that to L sine theta, and then we make the small angle approximation there. We say that the tangent of theta is just theta, and then we plug this in down here, and that's how we get that. Sorry, I just kind of skipped over that part. All right, so we're going to solve for our L here. Okay, that's how far away the screen needs to be. The W is in 3 millimeters, so I put that in meters. I got my aperture. That would be the value for capital D. And the lambda is what that wavelength is, and we get basically a meter. 0.97 would be the one that is, more. Well, if it was 1 meter, it'd be a little off from 3 millimeters, but that's it. So that's how bright that spot's going to be. Okay. All right. Let me see something here. All right, so let's look at more of these circular apertures. Now, having a lens set up, what will happen is if you have a wavefront that's parallel, like we normally want to set up for our interference things, and we hit a lens of a particular diameter, that does also represent an aperture. Okay, a lens is an aperture. What happens is the light gets bent and then gets directed down, and that produces diffraction patterns as well. I mean, if there was just a slit here, you got the same sort of result here. So having this large slit here, you basically can define a very similar thing, that the point at which this stuff comes down and reaches a focus is going to be the focal length of this. And so what we can do is we can consider an aperture of this size and then go through our equations and sort of work out what the equivalent thing of a lens is going to do here. So let's do that. All right. So in this example here, we have this big aperture here, and we're going to use our lens just really for the purposes of getting this thing to diffract down much faster than it normally would. I mean, if you have a really wide slit here, it's going to be very difficult to see that pattern, but the lens allows you to focus there to do that. So I mean, the same principle is going to apply here, whether it's a lens or an open in there. So we're just going to use the lens of the same size to produce the focused images over here. So it will produce a circular pattern as well, because while the light comes through, right, there's different dimensions to it. It is technically a circular shape that we're going to have here. So we will now here it's like a cross section. So this is just showing the intensity of light, but these are going to be rings here. That's the idea. All right. So this is the same relationship we had before then. Whether it's it's actually an open slit or it's a lens, again, same thing applies. And so the minimum size of a spot is going to correspond to 2.44 lambda f over d. Now, f is here because that's going to be our screen length, right? It's going to be, we're going to use that lens to focus the image. So the focal length, because remember the beams come in basic. There was some noise. What happened? Okay. Something made a noise around me. I don't know what happened. Okay, anyway. So, so the light comes in basically parallel, and so when it goes through the down to a focus, so the screen distance is got to be f. That's the idea. And so this kind of defines us for us here what that what the width of that's going to be there. Okay, and this, like I said, it basically incorporates an idea of a resolution here. So the same angle is going to be used here. And this represents sort of a minimum angular size, which is wavelength dependent, right? And so this is an angular resolution. Because any two parts of an image that would lie closer than the minimum angular size here, those are going to blend together. They will not be distinguishable from each other, so you can't resolve them. That's the idea. Okay, so question for you now. To focus light to the smallest possible spot, you should choose a lens with what? Any opinions on this? To focus light to the smallest possible spot, you should choose a lens with what? You want to drive, the idea is you're driving that angular size down as much as possible. Okay, let's see. All right, so yeah, that's the idea here. So you want to have smallest focal length possible and largest diameter. I mean, really, there's a wavelength dependence here, actually. Right? Wavelength dependence. In fact, when it comes to astronomical observations, if you've seen any really impressive images from space, 99% of the time you saw a Hubble image. And Hubble is very impressive because, one, it is in space, and it's a 2.5 meter diameter aperture. That's great. But what you may not know is that Hubble has the capacity to view in the ultraviolet and the infrared. The ultraviolet's good because that's a smaller wavelength. So it has an inherently better angular resolution. Okay. Now, you don't consider focal length and stuff for telescopes. We just really care about an angular size. Really, that's it. Yeah. I mean, yeah, absolutely. Yeah, totally. That works too with a magnifying glass. Yep. And that's why they make, like radio telescopes. Radio telescopes are enormous for a lot of reasons, but one particular reason is because the wavelength of radio telescopes are enormous. So you got to create a large diameter if you have any hope of getting any kind of resolution out of that. You generally don't get good resolution anyway. Even like the largest telescope period is the Arecibo radio telescope. It's a football field in length, and it's built into a mountain. It's in Puerto Rico, and even that doesn't have really great resolution. So, all right, so 12 centimeter diameter telescope is a focal length of 1 meter. What's the diameter of the image of a star in the focal plane? If the lens is diffraction limited, and the Earth's atmosphere is not a limitation. That's funny. All right, so we want the diameter, so we want our W here. Focal length is 1. We don't have a wavelength here. Why did I choose red? Oh, because red would be the largest width. If you choose anything smaller, it'd be smaller than that. So we'll just go with red. Red will look the worst. The diameter is 0.12, 14 microns. 14 microns. That's interesting. So that's how small it is. Now, what typically happens is this hits a CCD. And CCDs have pixel sizes to them. So it's probably, my guess is this is going to fall on a few pixels here. All right, so what's this? Yeah, a lot of CCDs are 4x4 micron pixel sizes. So this is going to fall on a few of them. That's why when you see in astronomical images, the stars have different sizes to them. But it's not related to their actual size. It's a lot of times just related to what's related to a ton of issues. One is diffraction. One is bleeding in the CCDs. Sometimes if you oversaturate certain cells, that signal bleeds into adjacent cells, especially depending on how the CCD is read. I mean, how's the signal processing? Sometimes you see straight lines. That has to do with how it's being processed. But anyway, so that's cool. There's also there's an intensity issue here too, which we're not discussing, but that's E&M stuff, so we don't get to that. Okay, so we got a camera lens with a focal length of 50 millimeters and a maximum aperture of it's an f2. It's big. Forms an image of an object 9 meters away. Okay. Resolution is diffracted limited. Great. Minimum distance between the 2 points that an object can be barely resolved. Okay. So the focal length divided by the f number. This is a relationship we had way back. That was actually that was the last lecture, I think, before the last exam. We went over cameras and things like that. So we had to define how to determine the aperture, focal length divided by the f number. And so that's going to be, for us here, 25 times 10 to the negative 3. So that's a factor of 2, so it's exactly half that. Makes sense. So what's the minimum angle that we're getting here? Well, we'll put our 1.22. We'll go with 500. Again, why am I going with 500? I mean, it's kind of right in the middle, sort of the visual spectrum. Just go with that, I guess. I mean, this number could be, honestly, I would accept anything in the visual spectrum here. 550, you know. Put our diameter in here, we get a very small, in radians, 2.44 times 10 to the minus 5. And we want to change that into a, like a separation, like a displacement between the points there. And so you might remember these equations again back when we did things with lenses, that the ratio of the object to image for both distances and size are the same. They're basically similar triangles here. And so we can equate these angles here. We do that. If we do this for the value for y, 22 millimeters, 0.22 millimeters is what we get for our value of y. And then I think for the next one here, we change this to f number 16, and that goes down a bit farther than that. So, oh wait, no, what did I do here? Oh, this was the distance between, this is the corresponding distance between image points. Okay, so the minimum distance between 2 points on the object is 0.22 millimeters. When it's projected onto the screen, those are the primes, and so this is extremely small, 0.0012 millimeters. So that would be the image. That's what we're projecting here. Whereas, so basically, what this is saying is that something that is, we could see something. We could basically see something that's farther apart than, say, 0.2 millimeters. And when it's projected on the screen, it will look this small. So the question then becomes, can you even see that, actually? Do you need another device for that? In fact, what's kind of funny, this is actually prior to the mid-70s or so, the way astronomical imaging was done, this predates the CCD, it was done with film. And film has amazing, just natural resolution to it, because you're literally just altering molecules on the film. And so the resolving power of those things were really, really excellent, but it generally produced images that were really, really, really small. And it was difficult to see these kind of separations in here. Okay, so there's a website I have up that likes to just occasionally scare me. Okay, trying to restore a laptop here. This boot disk has been in there for a little too long. Anyway, my point of the story was, I mean, your eye probably can't see down this far, but so interestingly enough, they'd produce these films from the astronomical imaging, and then they'd have to use a microscope to view a lot of that stuff. So it's kind of, I just thought that was always a very strange thing. And so there's all these, like when I was at UCLA, we had tons and tons of these big photographic plates and these microscopes that you attach to them to view things, and it was a very strange way to do astronomy. Anyway, all right, that's the next thing. Let's move on to that. We did this, we did this. Okay, so this gets into that concept of what's the minimum distance you can see detail in objects. So this last problem that we did kind of relates directly to what's happening here. This is what we were talking about, where these are the similar triangles. You actually have your objects with some separation between them at a certain distance s, right? And then the image is formed on a screen, and so there's an image distance and an image separation, basically. And these triangles are similar, so that's why we can make that proportion in the last question that we had there. But Rayleigh's criteria is a statement about how close because these two images here, so say these are two distant point sources, light or stars or whatever, they both will produce a diffraction pattern. Now the diffraction pattern that you see is extraordinarily small, and every point has a diffraction pattern to it. So if you have an image that's rich, you have trees and things, every single point has a diffraction, little ring to it. And those central maximums basically represent a pixel size, so to speak. But what happens is if you observe, say, point sources, not you don't have a lot of detail, just 2 point sources, they're going to produce 2 ring fringes. Very small things to see, but still, if they're not spaced far enough apart, their images will blend too much. And the question always becomes, what's the minimum angle that you can resolve the 2 things here? And this is what's called Rayleigh's criteria. So we go back to the same principle we had before, that this angular size has to be obeyed. And your angle, so when you work out in this picture here, the ratio of y to s and y prime to s, ultimately when you get something out of that, there's an angular size associated with that. And if your angular size is larger than that, then you get a resolved image. So like in this image here, we have minimum angular sizes for these 2 dots here, and if the angle between the centers of those dots are greater than that, then you're going to see both the sources. They blend together. Well, some of their rings blend together, but they're easily resolved. This is when it becomes an issue here. When the distance between the 2 sources in the screen matches the angular resolution, then it's called marginally resolvable. This is the absolute limit. If they were brought any closer, it would not be exactly clear that you're dealing with one source. Now again, that's assuming that we're dealing with point sources here. I mean, the issue becomes, what if they're not point sources? Then it's actually a little more challenging to do. And if these things are marginally resolved, I mean, maybe you're actually observing an object that's not a point source. That's some question there. So, and then if your angle is smaller than that, they will blend together. They will blend together, and you won't be able to see them. Again, I keep mentioning astronomy. It's my background. It's what my degrees are in. Well, graduate degree. I got physics degrees, but so if the angle's smaller, you can't see both the sources. Now, this is very common in astronomy because more than half of the stars in our galaxy are members of binary star systems. And those are 2 point sources. And guess what? They're pretty close together compared to how far away stars can be. And when we look at, let me show you this. Okay, so this is the Big Dipper. It's a little upside down from how you're used to seeing it, but the structure's there. And what's interesting about the Big Dipper is on the handle. If you look real carefully, you see these two stars real close to each other here. And if we zoom in on that, we get this picture here. And, these are two bright sources extremely close together in our line of sight. Now, it turns out that these stars are not part of a binary system, though. One of them is 3 times farther away than the other one. And this image does not tell us how far away they are. So we don't know which one is farther away. In fact, I actually don't know. I've never found out, just because it's always something I talk about in class I don't actually want to know. But this bright one could be farther away. We don't know. But here's what's interesting about these. Individually, these two stars are binary star systems. But their diffraction patterns overlap. They're too far away for their separation. And so that's how most binary stars look. You can't see that there are two stars there. There's other techniques you have to use to figure that out. Now you also see the spikes on here. There's spikes that go up and down. And then the circles that you see here, that's diffraction. The spikes largely come from, they're called diffraction spikes. It's a little bit more complicated, and it has a little bit to do with the CCD, because sometimes you see these at a diagonal, sometimes you see them up and down. It has a little bit to do with how the CCD processes the image, but the diffraction spikes are partially there because of diffraction. But anyway, so we could see multiple rings around these things. That's kind of neat. But unfortunately, these aren't resolvable. In fact, what's funny? When the Hubble Space Telescope went up, well, when it went up, it didn't work for like 6 months. That's cool. When it finally did work, though, one of the very first projects that the Hubble Space Telescope did was to just image tons and tons of suspected binary stars, because the resolving power of the telescope would be so good that they could see that. They could see those two sources there. All right, so we got two distant stars marginally resolved, viewed through a telescope having a 10 times eyepiece and a filter that only passes light at a wavelength of 500 nanometers. One way to resolve the stars would be to do what? What could you do to get a better resolution here? Very important question, actually. Anyway, sorry. What this is asking for here is we got two stars that we can barely tell apart. And we're wondering if you can improve the magnification or change the wavelength. C's and D's. Well, you're right. You need to change the wavelength. And you'll need to make the wavelength smaller, if you can. If you can observe with a smaller wavelength. And ultraviolet is a shorter wavelength. That's why I was giving you the story of Hubble earlier. So that would work. Okay. I mean, you don't generally have this luxury. Okay. And I'm glad to know that you said A and B. It's a really common misconception. Magnifying an object is not related to resolving power as much as those CSI shows want to make you believe that you can't super zoom on somebody's eyeball and then see another person's DNA, or whatever they do in those shows. Nope, zooming in does not improve resolving power. It just makes an object bigger and generally fainter, maybe a little blurry, things like that. All right, don't have to respond to this. This is just something we're going to talk through here. You've been asked to compare 4 proposals for telescopes to be placed in orbit above the blurring effects of Earth's atmosphere. That's nice. Rank the proposals in order of their ability to resolve small details from best to worst. Okay, so the radio telescope, you're not going to put that thing in space. But I'll still consider it. Right? You don't put radio telescopes in space. But anyway. 100 meters, my goodness. with a wavelength of 21 centimeters. That's not a lot. What you really want to do here, let me write this out. They're basically constructing a ratio here, you know. So let's just construct these ratios. Okay, let's draw this out. Okay, so you're doing your lambda. It's a 2 over 100. No, it's 2.1 times 10 to the minus 3. All right, fine. Infrared, 10 millimeters. That's quite long, actually. Over 2. What's this going to give us here? 5 times 10 to the minus 4. Well, that's better. Right, that's better. Remember, the angle here is it's 1.22 lambda over d. I'm just comparing lambda over d here. 500 nanometers, 5 times 10 to the minus 7 over 2. Well, my goodness, look how good this thing is, right? 2.5 times 10 to the minus 7. Put that radio telescope to shame. And then your ultraviolet telescope is a 1 times 10 to the minus 7 over 1. Well, we have our winner. It's the ultraviolet telescope. In fact, you just go up the list here. D, C, B, and A. And I should probably word this question differently, because it just so happens that the order of wavelength is the order of the answers. I mean, it does involve the diameter of the telescope. But, what? A and B? Did I mess up something there? Oh, yeah, I did, didn't I? Look at that. That's a 3, not a 4. Oops. Yeah, that's a 3 here. Well, it's messing up here. Anyway, sorry, that's a 5 times 10 to the minus 3, not a 4. So that is bigger. So it does go C, D, C, A, B. So that's not terrible, I guess. Can't do my orders of magnitude here. We got one more topic, and then we'll wrap this up, and I'll talk a bit about your exam after this. So let me get rid of the drawings here. All right, so one really interesting application here, which is seemingly very unrelated because it doesn't really involve sort of normal light that we work with here. It involves the X-rays, and it's called X-ray diffraction. And this is a technique where you actually can shine light on some sort of crystalline structure, anything with like a lattice going on inside of it. And what happens is the X-rays will come through, they reflect off atoms, and depending on path-like differences between individual atoms in the lattice structure, you actually can map out the lattice structure layout, what it is. You can work out an X, Y, and Z pattern in there. For example, you might have a substance where in one particular direction, maybe you have atoms more tightly packed, but then if you go in another dimension, they're more spaced out. And it's just the nature of how the materials are coming together in the solid there. But yeah, you should basically shine light onto crystalline structure, and then diffraction patterns come out from that. So the way this looks, and you can see up here how this is happening. Say we have two different layers of atoms here. We've got a layer up top and a layer on the bottom here. Now what happens is, as the light reflects off, in a given layer, everything is going to have the same length. Great. But if you take a layer that's underneath, the rays that come to the layer underneath and come up, as you see, can interfere with rays from other directions. For example, you can see here that, I'll draw this a little more bold, but an X-ray can bounce off this atom here and it can be completely parallel with an X-ray that bounces off this atom up here. And there's a significant difference between the atoms that are here, right? And so what happens is when that occurs, there is a significant path length difference. And so that path length difference is given by, d sine theta. It's basically the hypotenuse of this triangle here. The hypotenuse of this triangle, so if I draw the triangle out here, right, it looks like this, and the angle at which that comes off, that's the reflected angle. Those are all the same, right? So the difference in path is this distance right here, this hypotenuse, which is given by d sine theta. That's one way you can express that. And so there's a path length difference there, so that means there can be interference patterns that take place. There's a 2 here because the material has to come down and go up. So that's that distance d here. That's the distance between 2 different layers here. And so, I mean, whatever this thing here, just call this whatever you want to call it there. But ultimately, you're looking at the distance between 2 adjacent rows here. That's why there's a 2 here. And so what you can do is you hit this from different angles, and you can produce patterns of different orders here. And you can usually map out in a structure like this. You hit it from one direction, you go from the top, you go from the sides, you go from different angles, and you get a pretty detailed map of what's going on inside that structure there. So, let's see here, hold on. Okay, good. So we had an example here, I believe. Let's do that. Or do I? I do. Let's do it. All right. All right, so we got a 0.154 nanometer X-ray. We direct that at a silicon crystal. As you increase the angle of incidence of the beam from 0 to the first strong interference maximum, we had an angle of 34.5 with the planes. How far apart are the planes? Will you find other interference maximum from these planes at greater distances? All right, so the equation we work with is the 2d sine theta equals m lambda. We'll just go with an m equals 1 to start. And we put in a value for lambda, which is the 0.154 times 10 to the minus 9. We put in our angle that we're given here, and we get out a distance of 0.163 nanometers. So at this particular angle that things are reflected off of, that separation between the atoms there is 0.136. Now what you could do is, it says, will you find other interference maximum? Well, you throw in other values for m and see what you get. So we can actually create a relationship with m. So I'll just solve for sine theta here. We get m lambda over 2d. Well, lambda over 2d comes out to be this 0.56 number. And we have our m here. Now, remember, sine can't be bigger than 1. So first order works just fine. When we get the second order, we're over the value of 1. So we will not see another order produce an interference maximum.